Section 3.3, Harmonic Excitation of Underdamped Systems. So again, for the first thing we need to do is build out our system. We're going to have something very similar to before, where I've got a spring, and I've got a mass, spring stiffness K, X displacement to the right, capital F T here, and no friction on the bottom. But I know that if I have this, I can have a system that enters resonance and can go on forever. So that's not very helpful. So let's add damping to our system. And again, we're going to have C. Again, my free body diagram is going to be pretty simple. I'm going to have mass rollers, positive displacement X to the right. That's kind of a F of T. But now I've got a force acting back, F of K, which I had before. And now I have F of C, which I did not have before. So I got two forces acting back and to the left. So let's just make some adjustments to our previous equation and not having to solve through it all to add damping. So again, I'm going to have F of T is equal to F naught cosine of omega T. I've arbitrarily selected this, but I will tell you, if you arbitrarily select other potential solutions here, they'll cancel out and you'll end up with the same solutions, right? But we're going to say F naught cosine of omega T. And now I get an equation of motion that's mx double dot plus cx plus kx is equal to F naught cosine of omega T. Try to get a better C. So for convenience, right, we also want to write this in the standard form. And so that will be x double dot plus 2 zeta omega n x dot of t plus omega n squared x, well, let's drop this of t. I don't have it before, but you can have it there if you want. X equals F naught cosine of omega T. And again, that's a lowercase f naught because it's mass normalized. So we can say that F naught, just like before, is equal to capital F naught over M. So now I've got a solution. And again, I have a homogeneous and particular solution. X of t is equal to x of h of t plus x of p of t. X of h I know, that's my homogeneous solution. I'm not too worried about that. We've solved for that before in chapter 2. So it's x of p that I want. However, that's going to be a little bit different this time because I've got x of p is equal, you can have of t or not if you want, capital X, which I saw before, cosine of omega t minus phi particular, phi subscript p. And now the question is, why do we add that phi subscript p in? Because we know whenever I have damping, I get a phase lag, right? So I've got to have something there to compensate for the phase lag. So I'm going to put that in several places. So a little bit on this, not super important, but if you look at other texts, sometimes they'll use theta and theta p when they solve these out. A couple books do, some don't. I don't like the idea of changing parameters, but if you're following through with another text, sometimes you'll see that. I think phi is better, just to be consistent, but you quickly run out of Greek characters whenever you're doing math. So I totally understand why some people might do that. So I can write out my whole solution again. And that's x of t is equal to capital A, no subscript, e to the negative zeta omega n t sine of omega d t plus phi plus x cosine of omega t minus phi p. And this is my solution. So if you don't write much down, go ahead and write this down. Right? So again, our homogeneous solution is the exact same one we had before. Our particular solution is just adding in the x cosine of phi of omega t minus phi p. This would be x of t. Yeah. Okay, we can write this out in several different ways. Let's go ahead and solve through this. If I have x of p of t equal to capital X cosine of omega t minus phi p, I can split this up into capital A S subscript s of cosine omega t plus bs of sine omega t. This is from calculus, right? Just thinking back to calculus, breaking things apart. Okay, this becomes a little bit easier now if I need to do x dot of p is equal to, if I take the derivative of as cosine omega t, I'm going to get negative omega capital A subscript s sine omega t plus the derivative of bs sine omega t. I'm going to get an omega that comes out in front. I don't have a negative, and I still keep my b and s. And now I have a cosine of omega t. Now I can do the exact same to get my acceleration. X double dot of p. Still keep my negative. Now I get an omega squared. As sine goes back to cosine omega t. And now I get a minus omega squared bs. And I go back to sine of omega t. So if we think about this a little bit, the particular solution is a solution, and the homogeneous solution is a solution in their own right. And the equation of, so therefore the equation of motion can be used to describe just the particular solution. So let's just take half of that solution. and the particular solution and write it out. So again, what I'm starting with here in my standard form is x double dot plus 2 zeta omega n of x dot plus omega n squared of x equals f naught cosine of omega t. I've done nothing. That's exactly what we had before, right? I have an equation in motion. I have a solution. My solution is a particular solution. The full solution is homogeneous plus particular, but the particular solution is of and in itself a solution, so we can apply that here. And if I apply that here, I get quite the long term. So I get x double dot, which comes from here. I'm not going to write it all out, but I get x double dot, which comes from here. I get x dot, which comes from here. And then here, let's do some colors. I get x double dot, which comes from here. I get x dot, which comes from here. And I get x, which comes from here, equal to my generic f naught cosine of omega t, right? So we can easily rewrite all of that. That's not too hard. And then we can do a little bit of rearranging. We've got a lot of cosines. We've got a lot of sines that we can bring back into each other, right? So let's rewrite the entire equation and do a little bit of a rearrangement. And if we do that, you get negative omega squared, capital AS, plus 2 zeta omega n omega BS. Again, the first one's your natural frequency of the system. The second one is the frequency of your forcing function, plus omega n squared AS minus f naught, which is your mass normalized amplitude of your frequency. All of these terms were at one time multiplied by a cosine of omega t. And that's why they are all put together, plus all of the terms that were multiplied by a sine of omega t, which gives us negative omega squared bs minus 2 zeta omega n omega as plus omega n squared bs, all of that multiplied by sine of omega t, and all of that equals to 0. If we look at this expression, because we have sine and cosine, there's two special moments in time where cosine omega t and sine omega t are equal to 0, right? So if we set t is equal to pi, let me write pi up a little higher, over 2 omega, we get cosine of omega t is equal to 0. And sine of omega t is equal to 1. So that's very helpful. We can get this expression then, which is negative 2 zeta omega n omega, and I'm going to organize this as multiplied by AS plus omega n squared minus omega squared. I'm going to multiply that as BS. And I'm going to set that equal to 0. Now, if I do the same thing for t equals 0, at that point, I have t equals 0. I have sine, that gives me sine of omega n t is equal to 0, and cosine of omega n t is equal to 1. So again, that whole mess from before can be a bit easier. And rearranging a few things to get my AS's to line up, I can get omega n squared minus omega squared AS plus 2 zeta omega n omega BS is equal to 0. This gives me a nice system of equations, and we all know how to solve a system of equations. I can, oh, sorry, that's not correct, is equal to F naught. So I can solve a system of equations by just saying omega n squared minus omega squared. That's in the first spot. And then 2 zeta omega n omega negative 2 zeta omega n omega and omega n squared minus omega squared is equal to, sorry, AS, not equal to, BS is equal to F naught, lowercase f naught, and 0. So with that, we can get a solution for AS and BS. AS is equal to omega n squared minus omega squared multiplied by lowercase f naught over the common denominator, which is going to be omega n squared minus omega squared, this whole term squared, plus 2 zeta omega n omega squared, and one more solution, and BS is equal to 2 zeta omega n omega f naught over omega n squared minus omega squared, that whole term squared, plus 2 zeta omega n omega squared. Now, all we have to do to get a solution is to put it back in our triangle, use Pythagorean's theorem, and we can get a nice solution for x, phi, a, and t. If we think back again to our trigonomic functions, we can show that x is equal to the square root of as squared plus bs squared. And with that, again, from my trigonomic functions, I can show that phi p is equal to tangent inverse 1 of BS over AS. Whoa. So now I have a parameter for X and phi P. We can derive values for a particular solution now that are more interesting. We want to drop AS and BS so we don't have to solve those out every time. And so I can get capital X is equal to F naught, which is my normalized, mass normalized applied force, times the square root, it's a long one, of open parenthesis omega n squared minus omega close parenthesis, omega squared, close parenthesis squared, plus 2 zeta omega n omega, that whole term is squared. But I can get omega n, that's my natural frequency. Omega is the frequency of my forcing function, zeta, omega n, omega. So now I can get my x for the right-hand side of that equation. And I can do the same thing with phi p, which is equal to tangent inverse of a large fraction, 2 zeta omega n omega over omega n squared minus omega squared, and close that bracket. Let's clean that up. So what does that actually look like if I put this into an expression? Again, my expression is x of t. I'm going to put brackets here this time for clarity, is equal to x homogeneous solution, which of course is a function of t, plus x particular solution, which of course is a function of t. And so if I write out this whole solution, I get x as a function of t is equal to ae negative zeta omega n t sine of omega d t plus phi. So that's my homogeneous solution. That's going to eventually decay away to nothing, plus capital X cosine of omega t minus phi p. And that is my full solution. And so if you don't write much down, at least write that down. I guess I'm going to square a lot, but and that's a full temporal solution of our system. Okay, so if we look at the system, what happens when t gets large? Right? When t gets large, this a term is going to go to 0. And that means that x cosine of omega t plus phi really becomes our global solution. So we will often call so as t gets large, ae negative zeta omega n t sine of omega d t plus phi, the first part, that becomes your transient response. And it's transient because it's just passing through, right? It's going to be gone given sufficient enough time, or it's going to decay to a point where it's just trivial to the full solution. Vice versa, if t gets large, capital X cosine of omega t minus phi p, that has t inside the cosine, so that's going to continue to vibrate. It's going to oscillate. It's not a free vibration now, it's a forced vibration. And we call this our steady state response. Remember when we were forming this out, we said that a homogeneous solution is in and of itself a solution, and a steady state solution is in and of itself a solution, right? So this shows that as t gets very large, the particular solution itself is the solution that we're often interested in. And actually in vibrations, many times we will disregard the transient solution and only consider the steady state response. Okay, we have a cool equation here, which is quite long, but what do we need for it, right? We need some boundary conditions. So we could do x double dot of that and spend, hours doing this, or I can just write out the solutions for your boundary conditions. That seems like a much better use of time. So instead of taking the double derivative and canceling things out, let's just write this out. So if we have x naught is equal to 0 and v naught is equal to 0, just like every other time, we can get capital A is equal to x naught minus capital X cosine of phi p, and that's all divided by the sine of phi. And now we need phi, where we have phi, this one gets quite long, is equal to the tangent inverse. No, what do you do? Oh, let's draw a nice long line here. Put some brackets and fill it in. So we've got omega d, our damped natural frequency, parenthesis x naught minus capital X cosine of phi p. That's in brackets for the cosine, and then I close out the parenthesis that my omega d is multiplied by, divided by v naught plus, open parenthesis, x naught minus capital X cosine of phi p. Close out that parenthesis from before. That's this parenthesis here. Zeta omega n minus omega, no subscript, that's just our forcing omega, x sine of phi p. And that is our phase for our coupled solution of our homogeneous and our particular solution for force damping. And with that, you can solve out for any given moment in time where your mass will be, as long as you know your stiffness and your damping and your initial displacement and your initial velocity, which allows you to get a discrete solution for a vibrating system, considering both the transient and the steady state response.